Hello. Today we're going to talk about kinetic molecular theory, also known as KMT. This is a fundamental concept of molecular motion, and in particular, how temperature relates to molecular motion. And then we all understand that everything in our universe is either made up or of tiny little particles, atoms, molecules, things like that, or just vacuum space where there is nothing. But in most cases, in all cases, most tiny particles have some kind of motion to them because they have some kind of heat involved with them. And that's something that's kind of tough to understand. But I'm going to do my best to try to kind of explain that to you. Big thing is just recognize as we go through this that we are trying to understand how heat energy affects the movement of molecules and thereby affects the states of matter in our universe. Okay, first of all, we have to kind of state what is matter. So the definition of matter is anything that has a mass and takes up space. So it's got to have matter, it has to have mass, and it has to take up space. And it can basically exist in three states: solids, liquids, and gases. And we all know that solids are rigid in a fixed shape. Liquids take the shape of the container but have a fixed volume, and the gases can't have no fixed volume and can fill whatever container they're in. All right, so with that said, we have to have some key takeaways from kinetic molecular theory. There's some rules that we kind of have to think about a little bit so that we don't, well, to make a lot of what we're saying true, we have to pay attention to some parameters, and these are the parameters. I suggest you pausing the video and writing these down for notes. The first one is all molecules are in constant motion, unless the only way particles are not in constant motion is if we remove all the energy from them. And remember, we've talked before that energy always wants to move from high points of energy to low points of energy. So even if you remove all the energy from a particle, energy is going to be working back to it and cause it to start moving again. We call that absolute zero. That's negative 273 degrees Celsius, which is absolute zero, or 0 degrees Kelvin. When we hit that point, the molecule no longer has any energy and isn't moving. But molecules do not stay in that state for very long because something bumps into them and they start moving again. All right. We also have to deal with the fact that we have to think about gas particles having really no significant size to them when you compare them to the size of the container. We also have to make the assumption that when particles collide, no energy is lost and that they bounce perfectly. And then again, temperature relationship, the higher the temperature, the faster the particles are going to go. All right. So when we deal with solids, we're dealing with tightly packed particles. They have limited motion because they have bonds kind of holding them in place. So as it says there, strong forces, powerful attractions keep the particles together. As we add energy, as we see in these diagrams over here, the more energy we add, the faster these molecules will vibrate. And at some point, if we add enough energy, some of those bonds will break and it will become liquid. With metals, we have to get to several hundred degrees in temperature. With water, it's 0 degrees Celsius or 32 degrees Fahrenheit. And remember, solids have a definite shape. I'm going to throw up a state here and look at this real quick. If we look at this, we have a solid here, but notice the particles are vibrating very quickly. They just don't have a ton of energy. I mean, right now we have a temperature of 6 degrees Kelvin, which would be roughly negative 267 degrees Celsius, or over 400 degrees, negative 400 degrees Fahrenheit. All right. Well, watch what happens as we add a little heat to the molecules. They vibrate faster and faster, right? That is what kinetic molecular theory is all about. The faster the molecule, the more energy we add, the faster the molecules vibrate. Finally, we get to a point where they're kind of able to spread out. Down here, we're seeing what's starting, because they have the ability to flow around a little bit. They are now in a liquid state. We do have a few molecules that gain enough energy when they're in the liquid state that they pop off and become gas. But for the most part, now it has the ability to flow, and we can see the molecules kind of moving around and taking a volume of the container and kind of filling the bottom side of it. So how does that relate to what we have here on our slideshow? Again, liquids are in close proximity, but they're not locked into position. That's the biggest difference between liquids and solids. Liquids can flow and move. Particles slide by each other freely, and they will take the shape of the container. So the liquid particles maintain contact, but moving more freely than the solids. So they flow and adapt to their containers while keeping consistent volume, which we see in our simulation here. Now, as we add more heat, what do you think is going to happen to these molecules? I mean, we've already kind of talked about what happens when we add heat. The heat causes the molecules to move faster and faster. And notice, as I add a little bit of heat at a time, more molecules begin popping up into a gaseous state, and the molecules are moving faster. So that's kind of what you see happening when you boil water. When you boil water, the bottom water gets warmer than the water at the top. And what happens when you with water is, in boiling, hot air, just like hot water, rises to the top and the cold sinks, and that creates what is called a convection current, where it's spinning. The hot water is moving up, the cold water is moving down, and by doing that, that's what we see as the rolling boil. And I'm going to just go ahead and add a little more heat to this here. And as we do this, notice what's happening. More and more molecules are going to a gaseous state, and look what happens to our pressure has increased as well. As if we were to cool it down, let's go back the other direction. As we cool the molecules, look, the pressure backs down a little bit. Why is that? Well, pressure on the container is basically based on how often the particles hit the side of the container. So when we heat them up and they begin moving faster and faster, they hit the sides of the container more rapidly. And at some point, I'm going to continue to heat this up a little bit so we can have a little fun with this. At some point, we will get enough pressure or enough particles hitting the sides of the container that an explosion takes place. It's not happening yet, but we're getting closer and closer. Obviously, it takes some time to do this. Got to get this temperature going higher and higher. And because we have the finger, I guess it's not going to go ahead and blow the top off. It usually does. I'm not going to do that then. But notice when we went to adding more energy, the molecules move faster, and the faster the molecules moved, the more they became like a gas. So gases are particles that are in free motion. They can spread to fill the container. They no longer have any kind of bonds holding the molecules together. Yes, for example, water, H2O, the two hydrogens are still attached to the oxygen of the water molecule itself, but the water molecules separate H2Os are not attracted to each other anymore. They have enough energy that they are able to separate and move freely about the container. So there's almost no forces between the particles, and the particles will, obviously, the faster they're moving, the more often they will bounce off of each other, because molecules move in one direction until they hit something. When they hit the side of the container, they change direction. When they hit another molecule, they change direction. So that's a very important thing to remember as well. Now, if you think about that, it sort of makes sense that as we add, because basically temperature, I should say, is a measure of how fast particles are moving in a material. And finally, some key takeaways. Remember, particles are always in motion. We don't, we have, as science has been able to move a few hydrogen molecules to absolute zero, but again, they don't stay there very long. Remember that the states of matter are all based on the fact that as we add energy, particles vibrate faster, and solids have less energy, so they can stick together. Liquids, a little more energy, don't stick together quite as well. Gases, a lot more energy, and they can have the ability to overcome gravity and move throughout the container. So this is very important in understanding things like diffusion, pressure, and phase changes, things like that. That's why I created this video, was just to kind of give you a background as we go into our states of matter, into studying pressure, and even talking about phase changes a little bit. Thank you for watching this video. If you want to play with this little simulation, you just need to go to type into your Google search PHET, PHET. It is a simulation that you will find presented by the Education Department of Colorado. Thank you and have a wonderful day.